Okay, we flipped it over and I think it's a little better, but I still think I'm talking too rapidly. So I'm gonna really try to slow down here and uh, be more clear. If I have to mumble, I have a tendency to do that sometimes. Here's where we left off on hormonal control. So we talked about neural control of blood pressure and blood flow. Now we're talking about hormonal control. And mostly this has to do with changes in blood volume. So here's another way you regulate blood pressure by changing blood volume. I think I mentioned this earlier in this chapter. You can think of your body as this water balloon, stretchable water balloon. It has a certain amount of fluid in it. The more fluid in it, the higher the pressure inside. The less fluid in it, the lower the pressure. So you change the amount of fluid in your body will affect your blood pressure. Okay. First is talk about the renin-angiotensin system. Let me give you that in the next slide because that's a really complicated, practically whole body response to lower blood pressure. Aldosterone, basically, we could be talking about three hormones: aldosterone, atrial natriuretic peptide or ANP, and antidiuretic hormone, ADH. A little bit about epinephrine, norepinephrine, but that's going to be linked a little bit more to renin-angiotensin. So let's talk about these three right now: aldosterone, atrial natriuretic peptide, and antidiuretic hormone. Now, wait a minute. That's the, yeah, okay. So first, aldosterone. It's called a mineralocorticoid. If you remember from last semester, it comes from the adrenal cortex, and it stimulates the saving of salt. You lose less salt in your urine if your kidney secretes aldosterone. So here's the thing: if you are saving salt, you're not letting very much salt leave your body. Well, then what's that going to do to your blood osmolarity? It will raise your blood osmolarity. So in order to maintain blood osmolarity, you're going to have to reabsorb more water too. So if you reabsorb more salt from your kidneys, you're going to have to reabsorb more water to maintain blood osmolarity. So this means you reabsorb both salt and water, blood volume goes up, blood pressure goes up. Aldosterone also inhibits the reabsorption of potassium. So, I should say sodium. I shouldn't say salt. Sodium, well, usually when you think of salt, you think of sodium chloride. But there's other kinds of salt, so I should be more specific. It stimulates the reabsorption of sodium ions. Right? If you do that, you have to reabsorb more water. But it also causes the secretion of potassium. So and sodium and potassium go in opposite directions. If you reabsorb more sodium, you will lose more potassium. You absorb less sodium, you reabsorb more potassium. In fact, one of the biggest stimulations of aldosterone is too high potassium in your blood, because that can be really dangerous. Okay. Atrial natriuretic peptide secreted by your heart secretes this, and it is an antagonist to aldosterone. Remember, in the endocrine system, last semester we talked about hormone interactions. Synergistic, they do the same thing. Antagonistic, they do opposite things. Atrial atrial natriuretic peptide does the exact opposite of aldosterone. It causes you to lose more sodium and inhibit the reabsorption of water. So your blood volume goes down and it lowers blood pressure. So aldosterone raises blood pressure. Atrial natriuretic peptide lowers blood pressure by raising or lowering blood volume. Antidiuretic hormone. Remember, it's the hormone that will increase reabsorption of water through the kidneys. So if you're really dehydrated, you'll be secreting a lot of this stuff, and it makes your kidney tubules, distal convoluted tubule makes it permeable to water, and water will rush into your kidneys and will save water. We'll talk a lot more about that hormone actually in the urinary system when we get there, and actually how it works. So since it increases the reabsorption of water, your blood volume goes up, and so it also raises blood pressure like aldosterone does. But the one big thing different about ADH versus aldosterone, they both increase the amount of water you reabsorb, but ADH only increases the reabsorption of water. It has nothing to do with salt, with sodium or potassium. It's just water. So aldosterone has roles in reabsorption of sodium and potassium and water. But ADH just increases the reabsorption of water, has no effect on sodium and potassium. Epinephrine and norepinephrine are the postganglionic neurotransmitters for the sympathetic nervous system, and they are going to mostly what they deal with is the constriction of blood vessels. These are two hormones that will affect your blood pressure, but not by affecting blood volume. Like I said, a lot of hormones affect blood pressure by affecting blood volume, but not epinephrine and norepinephrine. They will cause an increase in overall blood pressure by causing vasoconstriction over most of the parts of the body, because they are the postganglionic neurotransmitters for the sympathetic nervous system. So if you secrete epinephrine and norepinephrine, and they're also from the adrenal gland, but from the adrenal medulla, you will it'll be acting like you turned on the sympathetic nervous system and raise blood pressure. And this will actually be, so we're going to look at now the renin-angiotensin system, and it has a link with aldosterone, and it has a link with actually constricting blood vessels. So let's take a look at that right now. And at this mechanism, which is really way too complex. I mean, we're going to do some simple things, but it's a really complex system. They use this to show how, why is it so complicated? Who knows? This is the way it evolved. And as long as it works, it's like then it's going to hang around. Okay. The first thing is kidneys detect low blood pressure or stimulated by the sympathetic nervous system. Either one of those, an enzyme called renin is released into the blood. Now, already in the blood, made in the liver, is an inactive protein called angiotensinogen. Renin will convert angiotensinogen from an inactive hormone to angiotensin 1, which is still an active hormone. Angiotensin 1 doesn't do anything. But what happens to angiotensin 1 is it eventually makes its way into the lungs, and a second enzyme called ACE, angiotensin converting enzyme, converts angiotensin 1 into angiotensin 2. And angiotensin 2, the strong increaser of blood pressure by three ways: causing vasoconstriction throughout your entire body, stimulating the thirst center. Now here, this system is going to affect blood volume, because the more you drink, the more blood volume you have. So it's going to make you thirsty. It's also going to affect blood volume by decreasing urine formation. You make much less urine, you lose much less water, and your blood pressure goes up. So the reangiotensin mechanism has both effects on peripheral resistance and blood volume. Okay. Let's look at blood velocity. Decreases from heart to capillaries and increases back to the heart. So this looks quite different from pressure differences from one side of the cardiovascular system to the next. Here we have elastic arteries, muscular arteries, arterioles, capillaries, venules, veins, and back to the heart being cable. This is blood velocity. It continually drops as you go from the big arteries to the small arteries. Why? Because the cross-sectional areas is becoming much more. It's as if you have a fast-moving river, and it breaks up into two tributaries. How fast is the water going in the two tributaries? Less than it was in the big river. The more blood vessels there are, the slower the blood goes. And when you get down to capillaries, you have more cross-sectional area capillaries than any other blood vessel. You have more capillaries than any other blood vessel. So the blood is flowing real slow through capillaries. And that's good, because that's where gas exchange occurs and nutrients exchange and everything. And you want time for that to happen, so you want the blood to go slow. As you go back, you get fewer and fewer blood vessels. Less venules than capillaries, less veins than venules. And so now it's as if two streams are coming together, and they go at a certain velocity, and when they get together, they go faster. So blood velocity increases as you go back to the heart. Not as much as it was when it left the heart, but it increases because the cross-sectional area is small. Okay. Okay, remember the role of the lymphatic system. One of the things the lymphatic system does a couple other things, and we'll talk about that in the next chapter, as a matter of fact. But it brings back excess fluid recovery from the tissues. Remember, only about 85% of the blood that leaves capillaries come on the arterial side comes back on the venous side. So 15% left over. That 15% goes into a lymphatic capillary and gets brought back to the venous side of the blood in the subclavian veins. Okay, local blood flow, blood delivered to capillaries. Remember, degree of vascularization determines how much blood gets to a particular tissue. And that's called angiogenesis. When we talked about one of the benefits of cardiovascular exercise is angiogenesis in your skeletal muscles. You make more blood vessels, you make a better blood delivery system. If you don't use them, you have regression, and blood vessels will deteriorate and leave. You have fewer blood vessels. If you put on weight, so making more and more adipose tissue, you have some angiogenesis there because you have more tissue. You got to bring blood to the adipocytes. Okay. Remember local regulatory factors in capillaries, particularly. Remember what opens and closes capillaries? Chemicals. In most tissues of the body, low oxygen would open capillaries or high CO2. High oxygen, low CO2 will close capillaries. And there's certain other chemicals that cause inflammation, like bradykinin. that will increase blood flow to capillaries. So that's called local regulating factors. So that's not really neural or hormonal, it's mostly like paracrines. Local hormones have that effect. And then remember, total blood flow is cardiac output, the same as cardiac output. Okay, variations in capillary function. Remember, in the kidneys, we have fenestrated capillaries, almost all filtration, almost no reabsorption. Lungs, it's exact opposite. It's all reabsorption and almost no filtration. There's almost no interstitial fluid in lungs, for reasons we'll get to when we get to the respiratory system. And so there's a variability in capillary flow and permeability depending upon whether the capillaries are open or closed, and whether there are certain chemicals in the environment. The edema is accumulation of fluid somewhere. How is that caused? If somehow capillary filtration is increased, and this happens in inflammation, then more fluid will come out of capillaries and the local tissue will expand. You have edema. Reduced capillary reabsorption. Something reduces how much reabsorption there is. Then blood fluid will stay out in tissues and you have edema. Or one really specialized thing is obstructed lymphatic drainage. If the lymphatic drainage is obstructed, then the organs and tissues drained by these lymph vessels will swell up. And this is why you should, if you go to Egypt and go to the Nile River, don't drink the water, because it's elephantiasis. It's these particular parasites that get into your body and enter your lymphatic vessels and obstruct them. So that doesn't happen here, but anyway. Okay, remember venous return, the mechanisms, there's always a pressure gradient between the blood vessels in your lower extremities and your heart. The blood pressure is greater out there than it is in the heart, and it flows back. Gravity will help venous return from the part of the body superior to remember the skeletal muscle pump and the thoracic pump. Skeletal muscle squeezing veins to help push blood back, and reduce pressure in your thorax and increase pressure in your abdomen when you breathe helps push blood back. And the cardiac suction, the opening of the heart during diastole, the increasing size of the vessels helps us suck blood back. Venous pooling is accumulation of blood in the limbs if somehow, and this happens in what's called congestive heart disease. Is if what if your left ventricle is starting to fail, then blood will start to pool in your extremities. If you have right cardiac failure in the right side of your heart, then that will cause pooling in extremities. Failure of the left ventricle will actually cause pulmonary edema. Okay. Okay, let's talk about shock quickly, and then we're going to finish. This is going to be the last vessels. Circulatory shock is a lack of perfusion, lack of oxygen being brought to the organs. There's cardiogenic shock, and that's a heart problem. The heart is starting to fail, and so blood isn't being pumped as much as it should be to organs. Then there's low venous return. It's hypovolemic shock, low blood volume, and that can happen actually if the large veins bring blood back to the heart, are expanding. And you have obstructive venous return of venous pool. Septic shock is infection over your body. Sepsis, it causes inflammation over your body, and this opens up blood vessels all over the body, and blood pressure drops, and you will get perfusion. Anaphylactic shock is the same thing. It's an immune response, but it's due to allergens. And then there's one that's not up there called neurogenic shock, when you have some damage to the cardiovascular center, brain damage, or damage to the vagus nerve, or some sympathetic nerves that affect heart rate, and heart slows down and doesn't perfuse enough. There's compensated shock and decompensated. Compensated is you lose a lot of blood. You can go into shock if you lose a lot of blood. So what your body does is constricts areas all over your body, increases blood to your heart and brain to keep those alive, and you're able to survive by those mechanisms that your body does. But they can only last a certain while. Decompensated is you've gone beyond that, but your blood volume has gotten so low, your body can't make adjustments to keep your brain and heart perfused, and this is death if something's not done. So emergency procedures are not done, that's death. Okay, finally, special circulatory routes. And it has to do with the most constant blood flow, most variable blood flow. The brain has the most constant blood flow of anybody. It gets its fair share no matter what. It gets a little bit more for exercising, but not that much more. And if you're not doing anything, and you're thinking about something, it gets its fair share of blood no matter what. Skeletal muscles is most variable. You're sitting there not doing anything, you're sedentary. You get there's relatively small amount of blood going to blood vessels. We saw in the other slide about 1,100 milliliters per minute. We saw strenuous exercise with the 12,500 milliliters per minute. So milliliters per minute. So it's really variable. It's the most variable. And then in the lungs, it's really unusual. Precapillary sphincters work opposite from all others. In the lungs, high oxygen will actually increase open capillaries, and low oxygen will decrease them. It's called ventilation perfusion coupling, and we'll talk more about that in the respiratory system. So that's it, folks, for this chapter. So we're all done. This is Vessel4. This will be the last one for this circulatory system. So long, we'll pick it up on the immune system, which is next.